Well, everyone, we are up for the next talk, and after having a quite virtualized morning today, we continue with virtualization procedures in general. Today with us is Michael Steil. He's the founder of the Linux Xbox project, and he's already spoken at some previous congresses, so you might know him. Well, virtualization in terms of VMware are around since 1999, and up to today we've only got VMware, Microsoft's virtual PC, and one, I think, Russian competitor. Now, the question is why 7 years of development only produced 3 software products. That has to do with some severe problems you've got to do when you virtualize computers. And Michael is going to give us some introduction about these problems and how to possibly solve them. Enjoy. And one thing, we're already a little bit behind of time, so please keep your questions for the end, so not to disturb the speech too much. Thanks.
Closer, so? Oh, now it's, yeah. Oh, it's louder now. Okay. Okay, so yeah, I'm Michael Steil. I've done Xbox hacking and all that, but that's not so interesting anymore. So I figured the entrance fee is too high for me, so I had to give a talk and had to prepare something. So I speak about VMware because that's some of my interest anyway. It's not only VMware; it's also Parallels. It's also virtual PC. But I think everyone knows the term VMware, so that was probably the best way to find a title. So what I'm going to talk about is why virtualization is interesting to us at all. Of course, virtualization is a nice hack. Many people use it. But the point is, why would you want to understand it? Are there some hacks involved? And the answer is yes. What would you want to know about virtualization? For all this, I have planned in some time about operating system basics, for all of you that don't know them. Then I'll talk about OS virtualization, why x86 is so broken, and how Intel and AMD have fixed that in the last generation of their products. First, let me tell you that I am not a VMware employee or anything, and all the information that I have comes from their open source code, because they have kernel modules that have to be open source because of Linux, or some other projects that are open source anyway, like Mac on Linux or QVM86 of QEMU. So let's look a bit at the history of virtualization products that we had in the past. VMware is the big thing. It has been existing since 1998. It was some startup company, and still today is the #1 for virtualization. Also on the market is virtual PC. It has been found, some guy named Eric Trout has founded Connectix. He's very well known because he did the first commercially successful dynamic recompiler, DR, for Apple for the 86K to PowerPC transition. And now virtual PC is owned by Microsoft. Also, there is a company, or there's a product called 2on2 from some Russian company, which works great with OS2. There's also Svista from some Russian company, which works great with OS2. There's also a product called Parallels from Russia. Funny things go on there. There's Plex 86. You might know the Box project by Kevin Lawton, who did this single-handedly himself. But the Plex 86 system, well, it failed. It never could run anything. But there's QEMU by another genius, Fabrice Bellard, who you might know of products like RZexe from the 80s. Or he also held the record of calculating pi to I don't know how many digits some years ago. And he also did QEMU. So virtualization seems to be some magic thing by some unknown startup companies, by some geniuses bought by Microsoft or some weird Russian companies. Those who can do it tend to write the same application 3 times, yeah. But my point is virtualization is something quite old. Or like this. This is an IBM System 360. And it has some tape drives here. What this system can do is about the same as this. Yeah, I had to find an excuse to put a C64 in my slides. I have to do that all the time now. These systems could do virtualization, maybe not virtualization as you know it, but the problem was, maybe you already know where this is going, that if a CPU is executing some code and it has to read from tape, it cannot execute any more code while it's waiting for a tape. So it has to execute, wait, execute. So in order to speed all this up or to make better use of the very expensive 1.33 megahertz CPU, you could do this. You could attach a second tape drive, and while the CPU was waiting, or one process was waiting for the tape drive, another process could just continue executing. And when it was waiting for the tape drive, the other one could execute again. So the more tape drives you added with this system, the better the CPU usage would get. Oh, and this is called multitasking. Maybe you know about it. Maybe you use it. But this is virtualization, because you virtualize your system. And this is all important for our virtualization term that we have today. So what it looked like was, in DOS times you had hardware and you had one single process, like a DOS application, with its hardware interface. And with an operating system, you have hardware and the operating system with its hardware interfaces sitting on top of that, providing virtual hardware interfaces to its processes, and several processes sitting on top of that, each with its own hardware interface to the virtual hardware. These processes are completely separated, as if they were running on a virtual machine. And they have their own virtual time. They all think they're running alone and have all the time, and their own RAM and their own I/O, basically. So that this separation works, we need two modes of operation for the CPU: supervisor mode, which has full control of the machine, and user mode for everything that cannot directly control the machine, but every time it wants to do that, it has to go through some code in supervisor mode, which is done using a trap, for example, the scheduler, which schedules between the different threads of execution or processes. Every time a system call, which is a virtualized I/O access, is done, and also access violations go from user mode to supervisor mode. Let's look at a timeline how scheduling works in this. This is all very trivial, but these are the basics to understand virtualization, because then it gets really complex. One process is running and it gets interrupted by a timer interrupt, then the system switches to the scheduler, which will then decide what process to run next. In this example, process 2, which will be halted by a timer interrupt again. Scheduler, another process, this time process 1 again, time interrupt, scheduler, process, and so on. This is called a time slice, the time of execution that one process has. And as you see, the system switches between user mode and supervisor mode all the time. The scheduler is a part of the operating system and runs in supervisor mode, and only it has full control of the hardware and can therefore switch between threads and all that. User mode cannot do this. So this is virtualization of time. We have to virtualize memory just as well. Every process has also the full system has the full memory in theory, because it's virtualized. We have we have several processes, each with its unique address space of the full 4 gigabytes, for example, but we only have one physical memory. So what we could do is to have a base address and a limit address and just map big blocks into physical memory. But a better idea is to, as you can see here, to map every, for example, 4 kilobyte page of any address space to physical memory. And some pages are just not mapped, you cannot access them. And also for the second process, so this is a lot more flexible. Now, virtualization is like an operating system of an operating system, because virtualization can, or virtualization as we call it today, can virtualize operating systems and not processes, so it is nested virtualization. While so far we had hardware and the operating system with its hardware interface on top of that, and the processes running on top of the operating system, with virtualization we have the virtual machine monitor with its hardware interface sitting on the raw hardware, providing virtual hardware. So this is the same picture as before so far, because we just have another level of virtualization. And what sits on top of the virtual hardware is this time not the processes, but complete operating systems with their hardware interface again. These processes, these operating systems have their processes running in them, and these operating systems cannot interfere with each other if the hypervisor doesn't want to allow that. So processes ran in user mode, and let's say they still run in user mode. Operating systems run in supervisor mode. But so what does the virtual machine monitor run in? Supervisor mode already has the complete control of the system, typically. So let's introduce a third mode, a hypervisor mode. Okay, this is just another excuse to have the German flag there. I admit it. But with three modes, there's no way that supervisor mode can have full control of the hardware. Of course, only one system can have full control of the hardware, only this can make it secure. So hypervisor mode is privileged mode, and the others are not privileged. So if something in user mode does something that user mode shouldn't do, it will trap. For example, the scheduler, if the time slice has come to an end, if a syscall is made to kernel mode, page faults and access violation will trap from user mode into supervisor mode. And also supervisor mode will trap for mostly the same events into hypervisor mode. For scheduling between the operating systems and not the processes anymore, the operating system. Also page tables, I/O accesses, or if the whole operating system crashes, then hypervisor mode will just deallocate the operating system but not crash the whole machine. So hypervisor mode, as I said, is privileged, the only privileged code on the system, and both user mode and previously supervisor mode, or well, it's still called supervisor mode or kernel mode now, must then be unprivileged. But what's the difference between user mode and supervisor mode if both cannot have full control of the system? Therefore, we could simplify the whole system and just call all this user mode, or just run all this in user mode and run all this in supervisor mode. So virtualization doesn't need three different modes of execution on the CPU. 2 modes are always enough, but 3 modes can be an optimization. Now let's have a look at how the different parts of the system interact here. If we only have two modes of execution. With 3 modes of execution, the last slide told you that user mode will talk to kernel mode, and kernel mode can talk to supervisor mode. But if we only have 2 modes of execution, it gets a bit more complicated. So in supervisor mode, there runs the virtual machine monitor with its hardware interface to the real hardware. And in user mode, we have the OS, which should normally run in kernel mode, but we now run it in user mode. The user mode has its hardware interface, which connects to the virtual hardware of the virtual machine monitor. And all the communication between the operating system and the hypervisor is done as on a 3-layer system. Any scheduler, page table, I/O, accesses, or crashes will be just communicated to the virtual hardware interface of the VMM. But what about all these? Oh, that slide is on the wrong page. Anyway, what this slide is going to say, this slide is supposed to be telling you how these traps work. For example, this is a real-world example of instructions that will trap, that just can not run in kernel mode on a hypervisor environment. For example, these instructions here taken out of, I think, Mac OS X, load some privileged registers of the system On a real system, this in kernel mode, this can of course happen, but not if you run all this in user mode or if you run this as unprivileged code. So what happens is with this LGDT, you get a trap. So the system goes into kernel mode, and the hypervisor can then emulate it with some pseudo C code here. The same is true with the next instruction. The third instruction is actually one that doesn't need any privileged accesses. That's just some calculation. It can just be executed. The next few also trap again. Yeah, so this is the interface between the operating system now in user mode and the hypervisor in kernel mode. But what about our processes? These processes think that they are in user mode, and they are, and they think the operating system is in kernel mode, but it isn't. So if a process with its kernel interface wants to connect to the kernel interface of the operating system, it doesn't work directly because it wants to talk to kernel mode, but the operating system is running in user mode. So what is done here is a trampoline approach so that every call gets intercepted. Well, anything that user mode wants to do with kernel mode will not go into the operating system, but will always automatically go to the virtual machine monitor, which will then detect what the operating system, what the process had in mind, and can dispatch this call to the kernel interface of the virtualized operating system. Whoa, this isn't supposed to be there. So what are the components, for example, of a VMware system? You have two components. One is running in user mode, which is the VMware executable, for example. And in kernel mode, you have another support kernel module, which is needed. The VMware main executable does all of the main logic. It does all the high-level emulation, like device emulation and boot up and BIOS devices, all these things. And you need kernel mode for all the mode switches. Kernel mode, user mode, mode switches, all that. You'll see that on the next slide. And also to intercept all the interrupts. All these things that just cannot be done in user mode must be done by a kernel module. Because if you have a virtualization system that runs on Linux, you have to put the kernel module under the GPL. Therefore, VMware and all the others try to put as much code as possible into the main logic in user mode, which they don't have to open source. So you cannot see all the interesting parts in that kernel module. So it only does what is really, really necessary. So let's have a look at scheduling again. We have these two parts, the VMware executable and the kernel module. Let's start with a big view of the complete system. The VMware binary gets a time slice. Time interrupts occurs, scheduler, another process gets run. The operating system scheduler, well, this is the scheduler of the base operating system or the hypervisor. In this case, what I'm telling here is that you run VMware on, for example, Linux, and not the VMware server thing, which has its own operating system. So this base operating system on which VMware would run has two processes here, VMware and a process 2, and schedules between these two. So each of them gets about 50% of the CPU. Now let's zoom in. What exactly happens if you run this VMware inside this VMware time slice? First, the VMware user mode binary will be run. It then switches into the guest code, so it donates it's almost the complete time slice for the guest code. And when a timer interrupt occurs, there's another switch back to VMware. All these switches are called world switches. So let's zoom in some more. At the start of a time slice, the user mode binary, VMware gets run in user mode. In user mode, you cannot do a world switch, because a world switch would mean you change all the registers, you change all the memory layout, you replace your scheduler, all that. So you have to do that in kernel mode. So the user mode binary switches into the vmmon kernel module, which can then do the world switch, run the guest code for example, now it's user mode code. Let's say you have, that's a Windows application that is running for one time slice on the hypervisor running on a Linux system. So this is user mode code also running in real user mode on the machine. Then, for example, this application wants to make a syscall. This syscall will be intercepted by something in kernel mode. So we have another world switch. The vmon kernel module will intercept this, will switch up to user mode into the big VMware binary, which has all the logic, and will decide what this was. Was it a syscall? Was it an interrupt? It will then decide and do what it thinks is right and switch back into vmon in this case, because we have to switch into virtualized kernel mode for the syscall. So there will be another world switch by vmon into guest code. Guest code is always run in user mode. And this time it is, for example, Windows kernel code, which is supposed to do something with the syscall. If the Windows kernel code does a sysread, returns from the syscall, we have yet another world switch into the kernel module. Kernel module will then hand all this up to user mode, which will hand it down again, do another world switch, and we are in the guest code again, in user mode, in our Windows application. So let's say at the end of this time slice, we have another time interrupt, which is supposed to run the base operating system scheduler again. This will again result in a world switch. Kernel module will hand it up, and it will in the end be handed to the system scheduler, which means the end of our time slice. So the whole idea of this donating a complete time slice to the guest looks a lot like with these world switches, you completely change the mode of execution. You change your complete world. That's why it's called a world switch. You get a time slice, you have to change everything to run something else which is completely incompatible, has a completely different memory layout, but at the very end, when there is a timer interrupt, you have to clean up, because the original operating system on which you're running has no idea about this virtualization thing. So this is like when your parents are gone and you want to have a party. Just when the bell rings, you have to clean up. So you have to intercept the bell, and you must make sure that your little brother doesn't intercept the bell and have them come in. So that is why we intercept the timer interrupt, or VMware does, with its kernel module. Let's zoom in some more. So what does a world switch look like? The world switch has to change really everything off the CPU. The register set, of course, because, well, that's mostly how it works with threads and processes on any operating system. Every process has its own register set, so we have to switch the register sets, including the interrupt vectors, so that the interrupts do not get intercepted anymore by the host operating system, but by vmon. And also the page tables have to be changed, because the memory layout of the guest can be completely different. So what does virtual memory inside the guest look like? So this is something just how it typically looks like. This is not something that virtualization imposes on how guest mode works, but typically you have some application code and application data at the bottom of memory, and at the top you have your operating system. So the interrupt vectors typically on a normal system point to some code in the operating system, but with virtualization we have to intercept the interrupts and not the guest operating system. The guest operating system cannot run in kernel mode. It could not intercept interrupts. That wouldn't work. Therefore, we add some page somewhere, some small page, and direct all our interrupt vectors there in our VMM code. We just map it inside the guest's in the guest's address space, so that we can do all these interceptions. So normally when you have a timer interrupt at the end of a time slice, the scheduler would run, but in this case this just wouldn't work, because we have completely switched worlds. All everything is completely different. The host operating system would have no chance to work because all the page tables are changed, all the interrupt vectors are changed, all the registers are not what it thinks they are. So that it would just crash. Therefore, we have to intercept it with vmon, do a world switch, go up into user mode, and now everything's back to normal. And the operating system, the host operating system, doesn't even notice that we have done so much. At the time slice start, it started some user mode program, and at the end of the time slice, we're back in the user mode program. So we can just let the scheduler run. Also, now this is a complicated one. You see, if you have, in this example, we have two operating systems with two applications each. If you only look at the left side of the slide, you have two address spaces, two processes on one operating system with their mappings. The second operating system also has mappings of memory into what it thinks is physical memory. So the operating system doesn't know about virtualization. It maps its guests' pages into what it thinks is physical memory. But of course, there's just one physical memory, and the operating system would all use the same pages. So we need another mapping between pages. This is what the hypervisor does. So every time the operating system, the virtualized operating system kernel, wants to do a page table mapping, it also gets intercepted and translated to the effective mapping, and all the page tables get updated to show the resulting mapping and not the intended mapping of the original operating system. But still, the operating system and user mode inside the virtualization will see the correct pages. So what about I/O accesses? This slide is supposed to build. It doesn't. Too bad. But I think you get the point here that if guest mode wants to do an I/O read, it also gets intercepted, because this is obviously kernel mode, because, well, on most systems only kernel mode can do I/O accesses. So this I/O access will also trap into the hypervisor. So a world switch will be done into vmon, which will hand all this up into user mode again, which will then decide what is going to happen and provide some fake result. For example, if this I/O read was the PS2 mouse device, and what about the mouse? Is there any change about the mouse? So it does an I/O read, and then VMware can fake this input. It can ask the host operating system, has the mouse really changed? Has it moved? Put all this together in a PS2 protocol and hand this packet down into vmon, and vmon will then hand it into the guest mode code, into the kernel of the virtualized operating system. So this is the theory. Now, how does it work on x86 on practice? Does it all work this way? So I've shown you two different approaches. One is with 3 different layers. For example, the G5 does it like that, or 2 different layers. Most other systems do it like that. So how does x86 do it? Do we have 3 layers or do we have 2 layers? And the answer is no. For example, there's this one instruction which can read whether we are in protected mode or in real mode. Normally, it should trap so that our VMM in kernel mode can emulate it somehow. But on x86, it doesn't. It just behaves differently. So if we have an instruction which is supposed to run in kernel mode, and we run it in user mode, and it traps, that's fine. We can emulate it, we can hand a faked result back. If it doesn't trap and just does something different, we can do nothing about it. And so effectively, kernel mode code might not work. So in practice, it also doesn't. If you try to run a Windows kernel or a Linux kernel without any change in user mode and fake the results with traps, it doesn't work. So what can we do about it? You've seen products like PowerPC or Virtual PC for Mac. They do emulation. You could always just emulate it. So every Turing-complete machine can emulate any other Turing-complete machine. You can have one big loop that dispatches all the different instructions, just emulate all these instructions, instruction by instruction. For kernel mode code, we could do that. We can run user mode natively because there's no problem with user mode. It still runs in user mode, behaves perfectly, and behaves the same, and we could just emulate kernel mode code. But this is just not optimal. We could do recompilation. Recompilation is a faster way of interpretation, and there are so many products out there that do recompilation. And all of them do recompilation from one CPU architecture to another CPU architecture. They just take binary code from, for example, 86K code from the Amiga emulator and convert it to x86 code, or PowerPC to x86 for PowerPC. And also the Xbox 360 has an emulator that converts old Xbox games to the new PowerPC processor shipping in the 360. So what VMware does is exactly the same approach, but it changes x86 code to safe x86 code. So it takes x86 kernel mode code and replaces, well, it can take most instructions verbatim. It doesn't have to do big translation of register sets and all that. It only has to see what instructions might be problematic and replace them with some other instructions or explicit calls into the hypervisor. So on this slide you can see on the left side what the original code would look like, and on the right side how it could be replaced. For example, some LGDT could be replaced by just calling some routine. This would be now be some user mode routine. We could also syscall into a hypervisor. That's a matter of implementation. And that's the same with the other ones. And those that don't have to be translated just can sit there verbatim. And while we're doing this anyway, we can emulate some things. And these are some, well, there is a performance impact by doing all this. If we had a not so broken architecture, then VMware could be a lot faster. But VMware is quite fast because it does do extra optimizations because they have all this infrastructure in place already. So normally if there's a syscall, I showed you that you have to go into vmon, it traps, it goes into vmon, it goes into VMware, it goes down to vmon again, and goes into kernel mode, into the kernel code of your guest code. But this can be optimized into this by staying in user mode, by staying in the guest code, by just replacing the syscall code with some other code that just does a small call, that just changes some registers or something, and then swaps into the kernel mode code without any world switches, without any context switches. If you think this is not safe because it changes the state of the emulated CPU or something, then keep in mind that all this changed code there is code that gets written by VMware, and user mode code or kernel mode code has no way to read this changed code back in and do any funny things with it. So there's some extra protection in place so that there's no way for user mode or kernel mode code inside the virtualization to find out that the code has actually been rewritten. Yeah, but the problem is this is quite complex. So VMware can do it, Parallels can do it, Virtual PC can do it, QEMU can do it to some extent, not so fast. But if you just want to have some small virtualization, for example, for PowerPC, there's the great Mac on Linux project, or also the Mac on Mac port, which isn't so complex, which is a product which has been existing for quite some time, and it works, and there's, well, except for QEMU, which is quite good now, there hasn't been an alternative for x86, because x86 was just too complex for all this. You cannot have lightweight VMMs for, there are many good ideas why you would want to have some VMM in some application. That is why both Intel and AMD introduced extra technologies with their newer CPU generations. I think most CPUs sold since this year include either VT or SVM technology. Well, it would be nice if there was just one technology, and it would be nice if it only had one name, but VT was called Vanderpool and is now called VT. SVM was called Pacifica and is now called SVM. So whenever you hear any of these, it's basically the same technology, but it is totally incompatible, of course. VMware, for example, can do both, and they have a very thin layer of abstraction between the two. It's just different opcodes. It's a bit different, but the system is the same. And the system, how it works, looks like this. It is a three modes approach. You have a user mode, a supervisor mode, and a hypervisor mode. So you don't have to fake anything. They could have changed, or they could have fixed the broken architecture just by making some instructions trap, which didn't trap in the first place. But this way, the hypervisor can still get a little easier. You can have some performance or some simplifications in your software with having that third mode. They call the hypervisor mode root mode, so the CPU will typically, if you boot up a system, the CPU will run in root mode, and if you don't use virtualization on, for example, the new Core CPUs, you'll run in root mode, and if you turn it on, the virtual machine will always run in non-root mode. And non-root mode will then have a supervisor mode and a user mode. So let's look at how VT, or also SVM, I'll stick with the example of VT, how it works in practice. Before VT, for example, world switches, well, the main point is that you can just very easily do world switches, either automatically or if you want to have an explicit world switch. Before we had VT, we had to use some code like this. We had to save all the registers, even the special registers, and we had to load a new register set from RAM, everything manually. Switching back, no, first this. Now VT only has one instruction for this. If you do vmEnter, you have one pointer that is already set up in a new special register. You do vmEnter, and on this pointer you have your complete register set, all the internal state. You don't have to care about the internal state, it's all managed by the CPU. You do a vmEnter, and it replaces, it saves your state and loads the new state. And it's then in guest mode. Runs the guest kernel until some interrupt or something occurs. Before VT, switching back to the host would mean you had to redirect all your interrupt vectors and have some small code mapped into the guest that could intercept all the interrupts and do the world switch back. And have some code like this again, saving all the registers and loading the old register set. With VT, everything you have to do is subscribe to interrupts. You have to tell VT what interrupts and what exceptions you want to have. Typically you want to have just all of them, that you can do good virtualization, or if you want to do very lightweight virtualization, like Blue Pill or rootkits, all these things, you don't want to have any interrupts. You let the system do everything, then it cannot be measured that you're running at all. Well, for most of the time, that is. You can just run the whole thing, and only if there is something special going on, like a keyboard interrupt or something, you can only intercept that single interrupt. So it gets a lot easier. Now what about speed? Does VT or SVM, does it really make everything faster? The point is that VT and SVM make development easier. For example, now we have Zen. Zen already supports both these technologies. Without VT or SVM, it cannot do it. There's so much extra complexity that would have coded into Zen, and nobody had done that. But it's not necessarily slower. It's not necessarily faster. That's the point. VT is not necessarily faster, and in some times it is slower. For example, VMware claims that their solution is faster than if they were using VT. For example, if you have the current version of VMware, any version of VMware, even on a VT-capable CPU, it will not use VT unless it really has to. For example, in 64-bit, there's some bug in AMD CPUs and also Intel. Well, AMD has fixed this bug, but Intel has not. So VMware has to use VT to work around this bug. So they use VT, but otherwise they don't, because they say without VT, it's faster. Because the key in being fast is avoiding traps. As I showed you on that one slide, if you want to switch between user mode and kernel mode inside the guest, you have to do so many world switches. if there is a trap. But if you do recompilation anyway, you can avoid all these world switches by just putting code in place that does the same thing. And all the solutions out there do this already, VMware, just like Parallels and all that. So VT isn't such a big deal. If you want to have fast virtualization on your system, you shouldn't really care about VT. If you want to code yourself some things that deal with virtualization, then VT is a great thing. Okay, that was my conclusion about VT and SVN and about virtualization in general. So if there are any more questions, I'm open for them now.
Okay. If vmware uses all this recompilation stuff, why does it still need a kernel module?
The kernel module is always needed to do world switches. For example, you want to change the memory layout. For example, if you're in the state that the VMware user mode application is running, then it has its specific memory layout. Then you want to switch into some Windows application, and this Windows application needs its specific memory layout. In a user mode application, you cannot shuffle the pages around as you want. You basically have to do a CR3 switch on Intel. You want to reload your page table. You want to completely change your memory layout. For this, you need kernel mode code. You cannot do this in user mode.
What you're saying is that QEMU works because it does more recompilation stuff, or what? Because QEMU doesn't need a kernel module?
That depends. I'm not so familiar with QEMU, but I think it has two different modes of emulation. If you don't have a kernel module, then it cannot shuffle around the address space totally, so it has to emulate this and is therefore slower. But QEMU has a mode with the QEMU kernel module which can speed all this up.
Okay, so it's just more recompilation and stuff.
If you don't have a kernel module, the recompiler will just do more and be slower.
Using vmware with recompilation will need more memory. And if you have applications that have a lot of code, then it can be noticeably much more memory what you need with VMware.
Yeah. Was that a question?
Yes.
Yeah, that's true. You have basically all the user mode code can be just executed verbatim, but all the kernel mode code has to be translated. So if you have a like 5 megabyte kernel or something in a system, also some data structures are duplicated. And also this is wired memory. You cannot just swap this memory out. This is expensive memory. Yeah. So without recompilation, you wouldn't need that.
So I've seen a couple pieces of malware that will jump to the middle of an instruction so that they get a different interpretation of that instruction because you're starting from a different byte. My question is, if VMware is doing translation from x86 to safe x86, do you think there's any potential for causing VMware to pass instructions to the processor that it thinks are safe but are in fact, because of some kind of contextual shift, unsafe?
I don't think I understand the question.
The question is basically...
Who understands the question? Oh.
Do you think there's any way we can make VMware execute unsafe instructions from the guest OS and the parent OS?
If VMware isn't perfectly safe, that is possible. It's a lot of code and it's very complex, and there may be ways to pass some instructions that VMware doesn't cope perfectly with. I think there have been exploits in the past, or there have been detections or something.
Cool, thanks.
Hello? Yeah. You have mentioned that the VMware server comes with its own operating system. To my understanding, it's not much more than a Red Hat that is sophisticated and comes with VMware. Or is there anything more regarding the layers of the system, hypervisor, supervisor, or whatever? Is the ESX server much different, or isn't it?
This is a very good question. I don't really know the answer.
I know some of the answer. The ESX server, it uses a modified Red Hat to boot up, but then it switches to a completely different root mode kernel. So it looks like Red Hat, but...
It switches to what? The doors open.
Oh, yes.
Anyways, sorry.
Yeah. The ESX server, it starts up with a modified Red Hat, but then it just loads the ESX kernel, which is completely different. It's not Linux based. Yeah.
Yeah, and this makes perfectly sense because it's a speed optimization as well. If you don't have to undo everything you do just to fake that nothing has happened for the operating system. If the host operating system is aware of virtualization, you can save a lot of cycles there. And maybe even complete mode switches. But one thing I haven't said that just comes to mind in terms of performance is running VMware actually really makes your host operating system a little slower, because every time there is some interrupt, it will not get handed up directly to the operating system, but it will first be intercepted by vmon and then get handed up. So if you're doing real-time stuff or high-performance stuff, maybe it's not a good idea to run another operating system in a virtual machine at the same time.
Hello? Have you looked into the traps that VMware has for like communicating with the actual VMware software from within, like the guest operating system? Like there's a couple of special instructions for detecting whether you're running within VMware, but there's also stuff like give me the physical resolution or change the physical resolution that the tools use. And apparently, I was just told that you can disable that, but it doesn't really work in all cases. Have you looked at that at all?
No.
No, okay.
Is there a time impact or a slowdown in having VMware just installed and its daemons running without a guest operating system running, or is it?
No. No. As long as you're not running virtual machines, vmon will never be called. So vmon is only called by the VMware executable, and it will then direct everything to itself. But as long as you don't run the user mode component, there's no sense in intercepting anything, no.
Thank you.
So for the various hardware devices that exist that you access from within a VM, like video, sound, USB, how many of them are full-on emulated devices that you speak to and then it speaks to the hardware, versus how many of them are actually doing direct pass-through of instructions from the guest OS to the parent hardware? Do you know?
I think that that depends on what actual implementations and what versions of the virtualization solutions you're talking about. So the desktop operating system of VMware don't support at all any pass-through to the host devices. I think the server versions do in part, for example, to have direct access to network cards. But all this is a security problem. For example, if you want to access a network card, the network card might be able to do DMA, and DMA is not done through virtual memory, but can talk to to memory directly, to physical memory directly, and if you allow some virtual machine to do that, it could override anything in any other virtual machine because it just doesn't know about that. So you would need either hardware that is aware of virtualization. For example, the vPro platform of Intel has a network card that is aware of that, and all the DMA accesses go through the MMU as well. Or you have to have some small layer in between.
So would you agree that you should not be using VMware as a security solution? Because a lot of people really want to.
I think I'd need more time to comment on that. Of course, it's always possible to exploit even complex software, and it surely should be possible to exploit a solution like VMware in some way. But the whole system, well, they had security in mind. They cannot pass through things for a security purpose. For example, I know one thing about VMware where there was a possible trade-off between security and performance, or security and not working at all. For example, the first AMD CPUs, the first AMD 64 CPUs, they, with their 64-bit mode, with VMware and Parallels, and I don't know, not Parallels, just VMware, they implemented having 64-bit guests as well. But as you might know, the first AMD 64 CPUs did not support that new version of VMware. They could do 32-bit virtualization, but if you had one of these steppings of the first AMD 64 CPUs, you could not do 64-bit virtualization. This was because of some bug in the first AMD 64 CPUs. Well, it wasn't really a bug. They omitted a feature that the 32-bit CPUs had, and they thought that the 64 CPUs didn't need anymore. But they didn't think of virtualization. So VMware had the choice of either not being perfectly secure, but being able to run 64-bit virtualization on these early AMD 64 CPUs, or just not run it all on these CPUs. And they chose that their solution just would not run at all.
And do you know how they do for like 3D hardware like DirectX or OpenGL or whatever? Because Wine, for example, translate the DirectX.
Microphone 2 should be open.
Oh. Wine translate, for example, the DirectX API to OpenGL calls, and do you know how VMware does that? Because I used VMware to play some games quite years ago, and I remember that it was quite fast, and I was wondering how they were doing it, like direct hardware access, and I doubt they're doing that because from a security point of view it would be a disaster, but I don't know.
It would be new to me that VMware can really pass through DirectX commands. I know that it can emulate some CPU, and maybe the drivers can do some basic 2D stuff, and Windows can then emulate all that, and maybe the machine was quite fast so that it was enough to do emulation of 3D. But passing DirectX through an interface, that's a really, really complex thing, and also for security that's a problem.
Thanks.
Hello. I've actually been watching you on the TV in the speaker room, and I ran all the way over here after I saw that the questions don't end because, well, I was about to ask a question, and then Danny here told me that everybody already knows about it. So, yeah. I wanted to ask your opinion about, for obvious reasons, to use VMM for ICE.
Huh?
Dan will help me out, because he already said, yeah, everybody knows about it.
So you can't do debugging as easily anymore because the code has all this anti-debugging stuff. So what have you seen with regards to using VMMs for debugging, like a GDB that lives outside of the host operating system?
I know that QEMU is a great debugging tool for operating systems because it is open source and all kinds of people have installed various hooks in there. And I know several projects that use QEMU for that. But I don't think that VMware has any hooks in there. So that's one thing that I've looked into myself. They want to do desktop virtualization, they want to do compatibility solutions, isolation solutions, server solutions, but development for user mode applications, but I haven't really seen VMware being used for kernel debugging or anything.
Well, maybe Dan is talking about VMware. I'm actually talking something like Joanna Rutkowska rootkit.
I'm sorry, I didn't understand.
Yeah, I'm not sure I want to repeat that. I'm actually talking about something the sort of like running ICE from something like Joanna Rutkowska's rootkit. Not really the rootkit, but the technology itself. Pretty cool. Think about it. Yeah, everybody laugh now, but wait just a few years.
Well, I'm really not sure whether this is the same type of question or comment as just before. This VT technology, does it make rootkits development easier? Are we going to see more lightweight rootkits such as Blue Pill in future due to VT or PELs?
This is a very good question. I'm glad you asked. There's a very good blog entry of one of the VMware developers on his blog, and he says that this whole Blue Pill thing just isn't worth the time thinking about it, because everything that Blue Pill can do can already been done today with other tricks. For example, with the tricks that VMware does. Of course, VMware is complex and VT makes it easier, but there are other tricks which don't perfectly virtualize the system and which aren't perfectly undetectable, but which are pretty much undetectable. For example, one good hack that you can do, which is almost as good as something as VT or Blue Pill, is that you can use a segment limit. Well, segmenting is something that x86 has been having for a long time, but nobody has been using it since modern operating systems. So you have a segment base and a segment limit, and you typically set the base to 0 and the limit to 4 gigabytes. But if you set the limit to 4 gigabytes minus one page, then you can put your own hypervisor, your own rootkit code into the uppermost page, and well, you are completely hidden from your host operating system. So you can direct all the interrupt vectors to you, all the exceptions to you. You can basically, in a way, virtualize the system already with a hack like this. It is not completely undetectable because it's not so perfect as VT. But also VT is very hard. It is very hard to make a solution with VT that is totally undetectable, because there is always some performance impact that you can measure. For example, if you have a CR3 reload, you can do a CR3, well, it can be cached, but if you load random values into CR3, then there will be a VM exit, there will be world switches, and you can measure these by time. Of course, your rootkit could fake your time, but then it gets very, very complex.
Well, as people didn't like my last one, I have a different type of question, which is less technical, but well, okay. Licenses, actual software licenses, have really been impacting the VM technology, because, for example, people would use the same hardware server, the same machine, to run, say, 5 IIS servers. And now everybody is changing licenses to say every single instant of the installation.
Yeah.
Now, there is a lot of stuff that can be done technologically. Do you believe personally there are technological ways that people are going to start using in order to cheat around that? And how do you think such licenses actually impact the technology, if at all?
So the question is whether there is a way to detect, no, to work around detection.
I'll give you the Gaudi translator. Hold on.
So, for example, the home versions of Vista have actually banned using virtual machines at all.
But is it just a licensing thing?
It is a licensing. Okay. It is a licensing issue, licensing thing. The question is, do you see licensing problems making it more difficult to legally use virtual machines?
Now, this is a political question.
It is.
I'm not going to answer political questions.
It's actually.
I'm an engineer. I'm not a politician.
It's actually a little bit technological, because licenses only cover very certain issues, and as there are different approaches to VM, would this cover, do you think, most of them, or are we going to see something that's going to happen differently now because of it, in your opinion? Or what are the engineering paths that can be taken?
Can you translate again? Thank you.
Basically, what kind of horrible hacks are we going to have to do to get around the legal barriers to virtualization?
Thank you! Dan fucking Kaminsky, everybody!
I just translate it.
That is a good one. Do they say CPUs? Do they say machines? Maybe you can have something like CPU affinity. If they say, for example, CPUs, you can only have it on, you cannot have more instances of this thing on one CPU. Then if you have a multi-CPU thing, you could bind one virtual machine to every CPU.
Okay, that's awesome.
Now Microsoft is getting ideas.
Can you detail how Xen compares to VMware?
Of what?
How Xen compares to VMware?
Xen and VMware are quite different solutions. VMware is always running on top of one operating system. Well, the workstation version is always running on top of one operating system, and also only the server versions have their own hypervisor and all the operating systems running on top of them. Xen has only the second approach. Xen is always the underlying thing, with one of the operating systems being the I'm not sure about the nomenclature, being the one operating system which can drive the actual hardware, and the other ones that are completely virtualized. So that's a very different approach of all that. Also, VMware has mostly been done for virtualizing mostly Windows, and any other operating system that you either don't have the source code for, so you cannot modify the operating system, or you don't want to modify the operating system because you just want to have your Red Hat disk and use that. And Xen is mostly, before VT, Xen has been done for pre-virtualized operating systems or para-virtualized operating systems. So the operating system that you run as a guest is aware that it is running inside of a virtual machine. So all these instructions that make problems won't trap, but they explicitly trap by calling the hypervisor. For example, there won't be something like a CR3 reload by move EAX, CR3, but it will be a call to the hypervisor saying, I would like to load another address space, which is easier for the hypervisor and which is also better for performance. So this is the whole idea behind Xen. So with VT and SVN, Xen can also do Windows virtualization or non-paravirtualized virtualization, but still the whole concept is more that of the VMware server version and not the workstation version. Yeah, Xen is cool, I agree. Yeah, I like para-virtualization because the whole... Okay, now comes one political thing. I think that the whole... This whole VT and SVN thing is just one big hack around the fact that Windows is closed source. Because if you have open source operating systems and all the operating systems that you would want to run inside of a virtual machine were open source, then there would be no need for something like that, because you could just modify the operating systems so that they are aware that they are virtualized. They're a lot faster, the hypervisor gets easier, and you can do a lot of nice hacks so that the host and the guest can communicate. It's only with closed source operating systems that all this does not work, and you need some workaround like VT or SVN.
Like at these places in public where I say,
Just one quick comment.
Windows is open source in a way that some people get the source of Windows, but they are not allowed to recompile it in a way that it can be paravirtualized.
Well, some people can read it.
They can read it, but they are not allowed to change it. I think there was a paravirtualized Windows someplace, but yeah.
Just
so
one comment.
Is this the sign that I should shut up?
No.
Nothing.
Just one comment on Xen and SVM versus VT. I spoke a lot to a Sun here. Oh.
Yeah.
Sorry. I spoke a lot to a Sun kernel engineer who works on virtualization, and what he claimed was that Pacifica helps them a lot to improve the performance with paravirtualization. So whereas VT is for them basically useless, running Solaris on Xen with a slightly modified Xen that makes use of all of the Pacifica functionality gives them a lot of performance advantage.
Yep.
So it doesn't really help in the virtual machine monitor case, but in the hypervisor case, Pacifica helps a lot.
Yeah, there's one thing. Well, VT doesn't really help. VT is really that workaround again around closed source. But SVM has one nice extra feature, and VT is going to have this feature as well in the future. I think the Intel's roadmap says, which is nested page tables. So there was one slide here that I don't know how to find again, but I think you can remember that slide about the two ways to, or the two steps to get from your virtual address inside a process to get to the virtual address of your operating system to get to the physical address of the machine. This has to be done manually by the hypervisor every time a page table entry is done. With a nested page table, this is a feature that only SVM has so far. You have two complete MMUs, which are which are one behind the other. So you can actually have your real page tables. You don't have to translate them. You don't get all the nasty TLB problems with that. And the hardware can actually do the whole thing, which will lead to a lot better performance. But VT will eventually have that as well. And this is one thing that not only real virtualization, but also paravirtualization can make use of.